Okay, so my original plan was just to attend this meeting, sit back, relax, and enjoy the talks. But I think Dheeraj asked me to give a talk, and again, the mid-semester has just started, and anyhow, so I've also had a very early start. So anyway, let's start with something very, very simple and very trivial, which all of you probably know it since your kindergarten. Okay, so what is this? This is a dark matter problem. You look at a rotation curve. The rotation curve is flat. Naively, what we expect from baryonic matter, from luminous matter, we expect a falling rotation curve. There's a rotation curve from this, expected rotation curve from a disk, from a gas, and then we posit the existence of a dark matter halo. So this is ubiquitous across all galaxies. Okay. Now, if you ask a different question, which is there any common property for all galaxies for which the need for dark matter arises? In other words, is there any property like distance, mass, acceleration, velocity, angular momentum, whatever? Now, if you look at plots like this, if you show the plots to, let's say, someone who doesn't know anything about dark matter or cosmology, that person will say, okay, the need for dark matter arises maybe above a certain distance. Okay, so at small distances you don't need dark matter. At distances beyond a certain point you need dark matter. Turns out that is not true. You look at hundreds and thousands of galaxies. For every galaxy, the need for dark matter arises at a different distance. Okay. Now the first person, if you look at if you ask the same question in a different way, okay, what you can do is you can plot the dynamical mass over the baryonic mass. So if the dynamical mass is equal to baryonic mass or less than the baryonic mass, then there's no need for dark matter. If it is greater than baryonic mass, then you need dark matter. Okay, if you plot something like this, okay, unfortunately it's not coming, I don't know why this portion is cut off, but anyhow, I think I've sent the PDF. Anyway, let me just move it. You'll see that the need for dark matter arises below a fixed acceleration scale, okay, 10 to the minus 8 meter per second square or 10 to the minus 10 centimeters per second square. Okay, so this is from an older plot, and this is again a rough analysis done by one of my undergraduate students. So basically you can see that the need for dark matter for all spiral galaxies arises below a fixed acceleration scale of 10 to the minus 10, 10 to the minus 8 meters per second square and or 10 to the minus 10 centimeter per second square. Now another thing you can do, right, if you look at the rotation curves, if you take the velocities and you plot that versus the baryonic mass for which you model it from disk, gas, and anything else, you see a nice empirical correlation. Okay, so the x-axis is the velocity, y-axis is the baryonic mass. You see a very nice correlation over 2 orders of magnitudes. Now again, naively, if you think about it, it's a little bit counterintuitive because for all dark matter dominated systems, I think dark matter constitutes about 90% by mass and baryons constitute only about 10%. So why should there be such a strong deterministic correlation between the total mass, between the baryonic mass and the asymptotic velocity? Okay, if someone told you that the dynamics of all planets in the solar system is governed by Pluto, you would say it's preposterous. Okay, but anyhow, so this is an observational fact. Another plot, yeah, can people at the back see the plots? Okay, yeah, okay, let me just go ahead. So in the 2009, it was shown by doing a core dark matter fit to a whole bunch of dwarf spirals, dwarf galaxy spirals, elliptical. The dark matter surface density is constant. The dark matter surface density is the product of the core density times the core radius. I think this is by fitting a Burkert profile. You can do the same to other isothermal profiles. You can do an NFW fit, you get something like this. Okay. So anyway, so this is a little bit disputed by some authors, but let's just go ahead. Okay. Finally, the money plot for all this is something called the radial acceleration relation. So the x-axis is the baryonic acceleration, and the y-axis is the total acceleration. You see this nice pristine deterministic relation between the total acceleration and the baryonic acceleration, which can be fitted by this non-linear function with very negligible scatter of about 0.1 dx. Okay, so in some sense, this relation subsumes all the other two or three relations I showed in the previous plot. Okay, so this is an observational fact. Okay, now I'll just make one sociological point, okay, which is that I think David Merritt has a nice paper in a philosophy journal where he surveyed through 40 books, textbooks in cosmology, structure formation, dark energy, and only one of them mentions both all the facts which I mentioned in the previous slides. Okay, so somehow I think there's a conspiracy that what he claims is that there's a conspiracy that students should not learn about it. And some of these textbooks include, some of these authors include Steve Weinberg, George Ellis, I think Martin Bourgeois, who's one of the pioneers of loop quantum gravity. Also, I think it includes, the Debashish Majumdar from Science Student. Also, it includes the book by Hoyle, Narlikar, and Burbidge, which presents a contrarian approach to cosmology, but even they don't mention it. Okay, so anyhow, so that's the. So what do you do? So the first, I think, Milgrom first proposed a modification to Newton's law such that below this acceleration scale, below which the need for dark matter arises. Okay, here it's actually, okay, no, here it's coming out fine, okay. He posited that acceleration goes as square root of the Newtonian acceleration. And so once you do this with one line of algebra, you can get the baryonic-Tully-Fisher relation. And in order to ensure a smooth transition between the two regimes, he posited this an interpolating function. So this modification to Newtonian gravity is called modified Newtonian dynamics, and it works remarkably well for galaxies. Now I should mention that Milgrom was not the first to propose a modification to GR to dispense with dark matter. Beatrice Tinsley did it in 1978. Joel Tolin did it in 1981. So they proposed 1 by R force law. But to the best of my knowledge, Milgrom was the first one who proposed a modification below this acceleration scale. Okay, so now obviously, before you sort of grill me, there are lots of problems in MOND. MOND does not work for galaxy clusters. This has been known for a long time. I think much below the bullet cluster. I think Simon White was the first to look at it. You calculate the MOND dynamical mass using whatever prescription Milgrom gave, that it's still much greater than the baryonic mass. You can crank up A0 and you can make it agree at one point, but it does not agree at all points. And again, there's obviously, I think, if you attend any particle physics conference, people always show the picture of bullet cluster. I think that has been a little bit oversold, but anyhow. And the main argument against MOND is that it does not agree with the observed matter power spectrum. Okay, now again, the main argument comes just with the observed matter power spectrum. It turns out that I think you'll get much more enhanced oscillations without the dark matter, okay? Another very strong watertight argument comes against this relativistic MOND theory comes from GW170817, okay? So I think in Subhadeep's talk yesterday, he talked about gravitational lensing of gravitational waves. A corollary of that is that gravitational waves also experience Shapiro delay. Now you have heard, must have heard many times that GW170817 shows that the speed of light is same as the speed of gravitational waves up to 1 part and something. It's slightly more nuanced than that. So that it not only tells you that the vacuum speed of light is same as gravitational waves, but also the line of sight Shapiro delay is same for both photons as well as gravitational waves. And that rules out a whole class of modified theories of gravity, which actually try to explain Milgrom's modified formula. So this includes Bekenstein's Tevez theory and few other theories. Okay, but I should mention that I think recently Scottis and Slosnick have come up with a new modified theory of gravity, which sort of explains the GW170817 and so on and so forth. Okay, okay. So basically, so what do you do? Okay, so there are two ways to deal with this. One is, okay, you just you ignore all of these successes of MOND at small scales, which is fine, which is what many people do. Another one is you sort of ignore all these problems of MOND at cosmological scale and just say that lambda CDM is host. So this is what a small fraction of the community does. You can also take a middle ground, okay, and say that, okay, cold dark matter is correct, but it better be able to explain, better be able to reproduce the observational successes of lambda CDM at small scale. So the first paper which sort of argued along this line is a paper by Manoj and Michael Turner. So I'll just read this aloud. So however, any successful theory of galactic dynamics must account for Milgrom's law. We show how Milgrom's law comes about in the cold dark matter theory of structure formation. So they gave an argument for why you get this preferred scale and so on and so forth. And since then, there have been many papers, including one by one of the SOC members, Asim. So Asim and Ravi Sheth wrote a beautiful paper where they did an ab initio derivation of radial acceleration relation from lambda CDM mocks. I think you were also, Teert also produced some of these mocks. At least the mocks paper, I think Teert was one of the authors. So anyway, so they talked about, they reproduced RAR from just adiabatic relaxation of dark matter halos from the gravitational wells, potential wells of the baryons. Okay. Okay, so the obvious questions to ask, at least for this talk, is I'm going to take a data-driven approach. So the edifice of MOND is the radial acceleration relation, okay? So let's see, let's try to shake it, break it, test it in different dark matter dominated systems, see where it fails, where it agrees, is the scatter same, is the scatter different. So these are some of the questions which I'll try to address, just observationally point of view in this class. So basically, does radial acceleration relation hold for galaxy clusters and groups? Is the scatter as tight as those for spiral galaxies? Does it hold for elliptical galaxies? The baryonic Tully-Fisher relation, does it hold at higher redshifts? So what about baryonic Faber-Jackson relation for elliptical? So I don't have a slide on that, but I just want to make one point, and I think so Yong Tien has done a whole bunch of papers where he has looked at baryonic Faber-Jackson relation for clusters, for groups, for BCGs in clusters. There's also one point which at least I don't understand. I think in 1980s there was a paper by Stu Shapiro and his students at that time who showed that globular clusters and elliptical galaxies lie on the same baryonic Faber-Jackson relation over 8 orders of magnitude in mass. Okay, now again, globular clusters don't contain dark matter, but elliptical galaxies contain dark matter. So why should they lie on the same line? Okay, so I have not seen a good explanation, or if there is, it's just my ignorance. Okay, so then are some of these relations consistent with lambda CDM? I already showed you some, pointed some reference. So I already mentioned how you can test this using gravitational waves. So last point I won't discuss. Okay. So so the first thing I will talk about is, I think let's test this with galaxy clusters and galaxy groups. So we tested this with a catalog of X-ray selected galaxy clusters in hydrostatic equilibrium. So this is the Wiklinen et al. Sample. So this is just some of the data. So I'll just show you the plots. I won't go through how we did this. You can just ask me. So x-axis is the baryonic acceleration, y-axis is the total acceleration. And, so these 3 plots are for galaxy clusters. This is for galaxy groups. The boundary between groups and clusters is a little bit is not sharply defined. So there's some overlap. So as you can see, unfortunately or fortunately, depending on what you want the answer to be, the points are all over the place. The relation is not very pristine. It's not very deterministic. And obviously, we don't have so many points over a large dynamical range, unlike for spiral galaxies. Okay, so anyway, this is how we did the regression. So I'll just I'll just try to summarize this. This is a little bit of a busy slide. So basically what we find is that if you try to fit for A0, it is about an order of magnitude larger for galaxy clusters compared to spiral galaxies. For galaxy groups, it is somewhere in between. The intrinsic scatter for galaxy groups is much larger, 42%. For galaxy clusters, again, for some of the works, it is small. I think Yongtian's analysis, where he has done the analysis using the clash weak lensing plus strong lensing sample, he gets a scatter as large as as much as for spiral galaxies, but and there's no consensus, there's no agreement between the best fit parameters also. Okay, so RAR cannot be universal, it's likely an emergent phenomena, it does not hold for clusters, and similar conclusions are drawn from by other authors also. Okay, just in case if you think everything I did is wrong, other authors also reach similar conclusion. Their results are also all over the place. Okay, so what about elliptical galaxies? So we did this for, again, we show baryonic acceleration versus total acceleration, and so this is the data for the elliptical galaxies, and the red one is the McGough et al. Relation, and the dashed line is the phi sigma load limit. So what we find is that it is much above the radial acceleration relation for elliptical galaxies. However, another group has also done the same analysis, Cha et al., which includes Mariangela Bernardi and Ravi Sheth. So they find that the results are consistent with spiral galaxies from the spark samples. Okay, so you can decide whom you believe. Okay, okay. So then I think with Gauri Sharma and my student Varenya, so we also looked at, we also tried to do baryonic Telly-Fisher relation with higher redshifts. Unfortunately, I think the data has the errors are slightly large. We have errors in both directions. So the fit is, it's actually even like there's regression in for errors in two variables is still a research in progress how to do it properly. But anyway, once we do it, we get a slope which is slightly different from 4. Okay, so this is at high redshift between 0.6 and 2.5. So this is, I think, the KMOS sample. Okay, so how much time I have? Okay, 1 minute. Okay, so what I will do, right, rather than rushing through the slides, I'll just present why this is important. I'll just flash the results and I'll just stop. Okay, so the surface density of halos, I think that is the plot which I showed, I think, of product of scale density and halo scale density and core radius, that which is constant. So beyond the test of MOND, it's also a very good laboratory for testing alternatives to cold dark matter. I think Lin and Loeb and Bondarenko showed that they use this to constrain models of SIDM. And I should also mention one more thing about SIDM. I think there's a paper by Keiichi Umetsu and his students who used radial acceleration relation of galaxy clusters to constrain some models of SIDM. Okay, so RAR can also be used as a test of SIDM, besides, of course, testing MOND. So Hayashi and Chiba used this to obtain a lower limit of mass of dark matter particles. So there's also a very nice paper by Andy Barker who showed that the fact that you see a constant halo surface density automatically rules out all models of fuzzy dark matter or ultralight dark matter. Okay, because there the halo surface density is not constant. The only way to get around this is obviously if you have some baryons or something, then you might obviate all these bounds. Okay. Okay, so I already mentioned this is a consequence of MOND. Okay, so what we did was we did the same exercise for clusters and groups, and what we find is that again, the product is about 10% larger. The scatter is much larger than for galaxies, and the slight deviation from perfect scale invariance. Okay, and finally, we also tested this with Asim's MOX, and we find that the halo surface density is I think the scatter is slightly larger, so it's both consistent with the constant halo surface density, as well as we cannot rule out dependence on as a function of mass. Okay, so I think that's it.